Right, then now we move to estimating sigma square. Okay, and then to do this, we just for now we assume beta is none. Okay, beta is no longer random variable. Okay, and this is my prior. Okay, this is my prior distribution of sigma square, and given sigma square and x, y is generated from this normal distribution. Okay, and our job is to figure out, or our job is to estimate the posterior distribution of sigma square. And to do this, as always, we compute its posterior density. Okay, to see what kind of density function it has. Okay, and just in case its density function is standard, that means it's a density function that can be found in any statistics textbook. Then we are done. Okay, and as always, this posterior density is computed by this Bayesian rule, and then this posterior density is proportional to the product of likelihood and prior density. And likelihood is the same as before. And now we have new prior density, which is density of the sigma square. Because sigma square follows an inverse gamma distribution, and then pi of sigma square, this prior density must have inverse gamma density, and it has this form. Okay. Okay, and then again, this inverse gamma distribution is defined by these two hyperparameters, alpha 0 and delta 0, and its mean is determined by, right here, delta 0 divided by 2 over alpha 0 divided by 2 minus 1. Okay, so this is expectation of sigma square. I would say posterior mean, or posterior expectation. Then here we know we know the functional form of the likelihood. This is just multivariate normal density, and then this inverse gamma density. Okay, and this is corner of normal density of y, and this is corner of the inverse gamma density of sigma square. Okay, so then here you can see the 1 over sigma square, and this is another 1 over sigma square. And here is exponential function, and here is another exponential function. Okay, so then we can put these together, and these two exponential functions together. Okay, and this is what we have. Okay, here capital T over 2 plus alpha 0 divided by 2 plus 1. That's why we have this. Okay, here this 1 over 2 sigma square, and here is another 1 over 2 sigma square. Okay, all right, and then this one, alpha 0 plus capital T, is denoted by alpha 1. Okay, alpha 1. Okay, let me, okay, here alpha 0 plus capital T is denoted by alpha 1. And this term, y minus x beta prime times y minus x beta plus delta 0 is denoted by now delta 1. Okay, here what this is, y minus x beta, what is this? What is this? Do we know beta? Yes, we know beta in this case, right? Because we assume that beta is known, beta is fixed. Okay, so then what does it mean by y minus x beta? This is just a residual. Okay, residual transpose times residual. This is RSS, residual sum of squares. Okay, RSS, residual sum of squares. Okay, sum of the squared residuals, right? Plus delta 0. All right. So then this is posterior density of sigma square. This is posterior density of sigma square, and then you see that this is very familiar. Why? look at this. This is what? This is prior density of sigma square, and it has this form. And this one and this one is very similar. The only difference is what? Here is alpha 0, alpha 1. Here is delta 0 and delta 1. And this is inverse gamma density. And then the distribution parameters are what? Alpha 0 over 2, delta 0 over 2. So then what about this? What about this? This must be what? This must be an inverse gamma distribution too. And what are the distribution parameters? Alpha 1 and delta 1. Then we are done, right? Again, we want to know the posterior distribution of sigma square given y. And to see this, we compute its posterior density. And then according to our posterior density computation, posterior density is what? Inverse gamma density. So that's why posterior distribution of sigma square is inverse gamma distribution. And then the distribution parameters are what? Alpha 1 and delta 1. Then we are done. This is how we estimate sigma square when beta is known. Okay, beta is known. Okay, beta is known. Okay, here. Okay, so then let's see. Okay, let's see. This is really important. Here, you see this conjugate prior. Okay, let me go back to the estimating beta here. Estimating beta here. Right? Okay, here. Okay, so this is the likelihood. This is prior for beta. Okay, and this is the your belief how y is generated. Okay, and suppose the y is still generated from this normal distribution. Okay, and now suppose you believe that beta is generated from t distribution or chi-square distribution rather than this normal distribution. Then in this place, in this position, it should be chi-square density, not normal density. Or this should be replaced by student t density, right? Then what happens? Nothing you can do. You cannot arrange this equation with respect to beta. Yeah, of course you can do, but this Cornell is something new, something you can't find in any textbook. That means what? This posterior density is not standard. Okay, it's not standard. You know it's posterior Cornell. Okay, Cornell, but it doesn't mean that you know the distribution of beta. Okay, this is really important. Okay, let me explain a bit more. Okay, a bit more. Okay, here, right? Suppose you have a dense function. Let me say f of x. Okay, you know dense function. But this is something new. And then how do you compute its mean? How do you compute its mean? Its mean should be computed by what? X times f of x integral dx. Right? This is expectation of s. Right? So even if you know the dense function, it's not easy to compute this integral. In special cases like normal density or t density or another standard distribution density, in special cases this integral can be computable. But in general, this integral cannot be analytically computed. Okay, you cannot compute this integral using just handwriting, right? So that means you cannot compute its expectation or mean of this random variable, right? So okay, here let me go back to here. Okay, so this is a density of the this is the posterior density of beta, and if this is not normal, if this is chi-square student t whatever, if this is something else, then we don't then the beta given y, posterior distribution of beta is not standard. Okay, that means we cannot compute its mean and variance, right? So then it's going to be very difficult to inference, right? So then only if this is normal density, then posterior density of the beta is standard. This is something that you can find in any textbook, right? So then this posterior density is computable, or we say that this posterior distribution is feasible only if your prior is normal, right? And this sort of prior distribution is called conjugate prior. Okay. So if the prior is conjugate, then posterior is standard, or posterior is feasible. Likewise, if this is not normal, if distribution of y is not normal, if this is t distribution or this is just chi-square distribution, something else, then still this is not computable, even if this is normal. So then posterior distribution of beta is not standard. Okay, but whenever we say conjugate prior, then this prior this f of y or the likelihood is usually normal, but not always though. Anyway, given the likelihood, depending on your choice of the prior distribution, the posterior can be feasible or not. Okay, so if the likelihood is normal, then if your prior for beta is normal, then posterior is feasible, and this sort of prior is called conjugate prior. What about sigma square? Conjugate prior for sigma square is inverse gamma. Okay, inverse gamma. If this is the inverse gamma, if this is chi-square, then posterior distribution of the sigma square is not standard. Okay, so to get analytical solutions, or to get these solutions by handwriting, then priors should be conjugate. Okay, this is really important. Okay, right?